Welcome. In this session, we'll walk through the design of a video recommendation system, the kind that powers personalized homepages on platforms like YouTube or Netflix. Our goal is to understand how machine learning can help recommend the right videos to the right users at the right time. We'll cover everything from framing the problem and preparing the data to developing and deploying the model at scale. Let's dive in and see how all the pieces come together to build a production-ready recommendation system. As before, we follow the same framework. First, we try to clarify the requirements by asking the right questions. Then we frame the problem as a machine learning task with a clear machine learning objective. We prepare the data, develop, evaluate, deploy, and serve the models. The problem is to recommend videos on a user's homepage based on their profiles. Here are some good questions to ask in the requirement clarification phase. Can I assume the business objective here is to increase user engagement? Are videos in different languages? How many videos are there? How fast should the system recommend videos? ML objective: maximize the number of relevant videos shown. The primary machine learning goal here is to rank and recommend videos that are most relevant to the user. Relevance can be defined in many ways. Product managers, PMs, may define it based on clicks, watch time, completion rate, or some custom combination. Ultimately, the system should maximize user satisfaction and platform engagement through these relevant video recommendations. Input: a user profile. The ML model takes a user as input, which includes demographics, history of interactions, and current context, like time of day, device type. This forms the basis of a dynamic representation of user preferences. Output: a ranked list of videos. The model doesn't output a single video. It outputs a list sorted by predicted relevance scores. The top K videos from this list are what the user will see on their homepage. Recommendation strategies: content-based filtering. This strategy analyzes the content of videos the user already engaged with. Example: if user A liked videos X and Y, and video Z is similar to X and Y in terms of metadata, visual features, or embeddings, we recommend Z. Works well for new users or those with very specific preferences. Collaborative filtering. Instead of focusing on content, it focuses on similar users. If user A and user B have similar histories, and B watched a video that A hasn't seen yet, we can recommend that to A. Effective at capturing latent trends and group behavior. Hybrid filtering. Most real-world systems use a hybrid approach, combining content and collaborative filtering. This helps overcome the limitations of either method alone, especially with cold start or sparse interaction data. This problem framing allows us to move toward model development, building a system that learns to match the right content with the right user at the right time. Again, there are two parts to data preparation. 1. Data engineering videos. The system ingests a large catalog of videos. Each video is associated with structured data such as ID, upload timestamp, duration, and unstructured metadata like title, tags, and description. Users. Every user has a unique ID and associated profile data. We capture attributes such as age, gender, country, and sign-up date. This forms the static user profile. User video interactions. This is one of the richest sources of signal. We collect explicit feedback, likes, dislikes, shares. Implicit feedback, watch time, video completion rate, clicks, impressions. These are critical to learning what types of content each user engages with. 2. Feature engineering video features. ID. Useful as a categorical identifier in collaborative filtering. Duration. Helps determine user interest in short versus long-form content. Title and tags, encoded using NLP models, e.g., TF-IDF or BERT, to provide semantic information for content-based filtering. User features, Demographics. Age, location, and gender can influence content preferences. Contextual info, time of day, device type, or network connection can affect watch behavior. Historical interactions. Long-term, across weeks, months, and short-term, current session interactions are modeled to capture evolving interests. Matrix factorization is one of the foundational approaches in recommendation systems. It works well when you have a large amount of interaction data between users and items, in our case, users and videos. We begin by constructing a user video feedback matrix. Rows represent users, columns represent videos. Each cell in this matrix represents the user's feedback on that video. This feedback can come in multiple forms. Explicit feedback, such as likes, shares, ratings. Implicit feedback, more commonly used, including clicks, watch time, skip behavior, and even dwell time. Because users only interact with a small subset of available videos, this matrix is extremely sparse, with many missing entries. And our goal is to predict the values of these unknown entries to recommend the most relevant content. The model matrix factorization assumes that both users and videos can be represented in a shared latent feature space. So we decompose the feedback matrix RR into the product of two lower rank matrices, RUVTR JAPROX U ANSI dot, VTUU, the user embedding matrix, where each row is a latent vector representing a user's preferences, VV, the video embedding matrix, where each row represents the features of a video. The dot product UIVJU I and C.VJ estimates how relevant video JJ is to user T. Training involves randomly initializing the user and video embedding matrices, iteratively updating them to minimize the difference between the observed values in the feedback matrix and the model's predictions. This is done using optimization techniques like stochastic gradient descent, SGD, or alternating least squares, ALS. Loss function. There are three main loss formulations: observed-only loss, minimize squared error only on known user video interactions, fast but ignores non-interactions. Observed plus unobserved loss. Treat unobserved entries as negative signals, useful for implicit feedback. Weighted hybrid loss, weigh observed interactions more heavily than unobserved ones to balance learning. This helps account for uncertainty in implicit feedback, e.g., not watching a video doesn't always mean disinterest. Optimization. Two popular methods, SGD, easy to implement, scales well, but sensitive to hyperparameters. WALS, weighted alternating least squares, designed for implicit feedback and scales well in parallel environments. The choice depends on system constraints, e.g., real-time versus batch, distributed infra, feedback type. Inference. Once trained, inference is efficient. For any user, retrieve their embedding. Compute the dot product with candidate video embeddings. Rank videos by score and return the top N. This low-latency retrieval makes matrix factorization suitable for large-scale recommendation systems. Pros: scalable, training and inference are both efficient. Compact, only need embedding vectors for scoring. Well understood, easy to implement and analyze. Cons: no use of metadata, doesn't leverage features like video title, tags, or user demographics. Cold start problem: performs poorly for new users or videos with no historical data, assumes linear interactions, can't model complex or non-linear patterns unless augmented. In modern systems, matrix factorization is often used as a component, for example in candidate generation, combined with other methods, like deep learning models or content-based features in later stages for ranking. This combination of simplicity, scalability, and interpretability is why matrix factorization remains widely used, especially when bootstrapping a recommender system. Let's now discuss the two-tower deep neural network, a popular approach for scalable video recommendation systems. It's particularly suited for candidate retrieval, the first stage where we quickly identify a few thousand relevant videos out of potentially millions. 2. Encoder towers. The model consists of two separate neural networks. User tower takes user-related features, e.g., demographics, historical watch behavior, device type. Maps these to a fixed-size user embedding. Video tower takes video features, e.g., title, tags, metadata, categories. Outputs a video embedding. The idea is that both embeddings live in the same vector space, so we can compare them directly. Relevance via embedding similarity. The distance or similarity, commonly dot product or cosine similarity, between the user and video embeddings represents how relevant that video is to the user. During training, we optimize this similarity to be high for positive interactions and low for negative ones. Dataset construction training data is made up of user-video interaction pairs. Positive pairs come from implicit or explicit feedback, e.g., clicks, watches, likes. Negative pairs could be sampled randomly or drawn from unclicked recommendations. Data imbalance is common, far more negatives than positives, which should be addressed either via sampling strategies or weighted losses. Loss function. We use standard classification loss, such as binary cross-entropy, where the model learns to distinguish relevant from non-relevant videos. More sophisticated approaches, e.g., contrastive loss, sampled softmax, can also be used in large-scale systems. Inference. Classic nearest neighbor problem. Once trained, you pre-compute all video embeddings and store them in an index. At serving time, you compute the user's embedding on the fly. Then you perform an approximate nearest neighbor search to retrieve the most relevant videos based on embedding similarity. PROS uses rich user and video features, not just ID-level interaction, handles cold start users better than pure collaborative filtering. Flexible and modular, can plug in different architectures, e.g. transformers. Cons, slower serving. User embedding must be computed in real time. Training is expensive, too large encoders and more parameters. May require distributed training infrastructure at scale. This architecture forms the backbone of many industrial-scale recommender systems and is often followed by a second-stage re-ranking model to fine-tune final recommendations. In this phase, we evaluate how well our recommendation system performs, both offline during model development and online in a live user-facing environment. Offline metrics. These metrics help us assess performance using historical data before deploying models to production. Precision TK. This measures the proportion of the top K recommended videos that are actually relevant to the user. It helps us evaluate how useful the top results are. Mean average precision, EMAP. MAP considers the order of the correct recommendations. It's the average of the precision scores at the positions of each relevant video. It gives a fuller picture of ranking quality. Diversity. This metric measures how varied the recommended videos are across different topics or genres. A model that always recommends similar content may have high precision but poor diversity, leading to user fatigue. Improving diversity helps maintain engagement over time. Online metrics. These are used to evaluate how the system performs with real users in production and reflect actual user behavior. Click-through rate, CTR. CTR measures how often users click on recommended videos. It's an immediate proxy for relevance and appeal. Number of completed videos tracks how many of the recommended videos are watched to completion. A higher value suggests better content alignment with user interest. Watch time, total time spent watching recommended videos. It's a strong indicator of user engagement and satisfaction. Explicit user feedback includes actions like thumbs up, down, ratings, or surveys. While sparse, this feedback is very high quality and directly reflects user preferences. In summary, a combination of these offline and online metrics helps us not only tune model performance, but also ensure the recommendation system delivers a satisfying and engaging user experience in the real world. Let's now walk through the serving pipeline, which happens in real time as users land on the homepage. It's typically split into three main stages: candidate generation, scoring, and re-ranking. Candidate generation. The first stage is about efficiency. We need to narrow down from billions of videos to a few thousand that are likely to be relevant. This is handled by a lightweight model, typically a two-tower neural network. The towers encode the user and the video separately, and then use embedding similarity, like dot product, to retrieve top K nearest neighbors for a user. This model prioritizes speed and recall over fine-grained ranking accuracy. Scoring. The second stage is where we score the candidate videos more precisely. Here, the system takes the user features and the candidate videos as input and outputs a ranked list based on predicted relevance scores. Again, we often use a two-tower architecture, but this model can be heavier, with more parameters, deeper layers, and richer feature inputs. This step focuses on accurately estimating how likely the user is to engage with each video, whether by clicking, watching, or sharing. Re-ranking. Finally, we apply re-ranking logic to adjust the final results. This step takes the top-ranked list and refines it by incorporating business rules or social constraints. For example, we may apply fairness constraints, promote new or diverse content, or penalize certain categories to reduce bias. Re-ranking is where we balance user preferences with platform goals, such as safety, diversity, and creator exposure. Together, these stages ensure that we deliver relevant, responsible, and performant recommendations, all within a tight latency budget to maintain a seamless user experience. Let's walk through some of the key challenges we typically face in building and maintaining a homepage video recommendation system. First is serving speed. Because we're dealing with billions of videos and millions of users, latency is critical. To keep the system responsive, we use a two-stage design. The first stage is a lightweight candidate generation step that quickly narrows down the universe of videos to a few thousand likely candidates. The second stage is a more heavyweight scoring model that ranks these candidates in finer detail. Second, precision. Even with the right candidate pool, we need to ensure that the top results are actually relevant to the user. That's where the scoring component comes in. It uses complex models like neural networks to rank videos by predicted relevance. Fine-tuning this for high precision is an ongoing effort. Next, diversity. A common issue in recommender systems is echo chambers, showing the same type of content repeatedly. To combat this, we use multiple candidate generators, each designed to pull in different types of content. This helps balance relevance with variety. Cold start problem. This affects both new users and new videos. For new users, we don't yet know their preferences, so we rely on user features, such as demographics or device, and use two-tower neural networks to make early predictions. For new videos, we initially show them to a small, randomized audience to collect interaction data, which we can then use to train the model. Finally, training scalability. Our neural networks can be large and complex, especially with millions of users and videos. We address this with a modular design that allows for fine-tuning, rather than retraining from scratch. This helps us iterate faster and update the model more frequently without full-scale retraining. So, while these challenges are real, they are manageable with the right system design and infrastructure.